And moving on to chapter 12. Again, this is part of week 6, and we're going to be talking about quantifying uncertainty. So, as the name implies, uncertainty definitely has a statistical component. So, we'll start off by basically doing a bit of, first of all, we'll talk a little bit about it, and then we'll jump into kind of a refresher. So, what is an uncertainty, and what does it kind of imply? So there's a general situation, right? So you have observable variables. This is evidence that the agent can actually know the value of in a given environment, given world. So that means it's things like sensor readings, symptoms if you're diagnosing a disease, and so on. So it's known. There's no hiddenness to it. That's compared to the unobserved variables. These are things that the agent can't necessarily see or percept, but it is things that exist and can be reasoned. So it's something that can either be done through some form of inference or whatever. A model is how the agent knows something about how the variables that are known to each other relate to those which are unknown. So it's a way of figuring out an unknown variable given a set of known variables. And probabilistic reasoning gives us a framework for managing our beliefs and knowledge. So it's a way that we can combine these things together and essentially derive information from things which we um, maybe cannot see, but based upon things we can. So kind of jumping into some basic probability notation, and here's that review portion of statistics, right? So I'll go over this fairly quickly because hopefully you guys have all had statistics along the way. And by guys, I mean guys and girls because it does not denote gender. But anyway, jumping back in, random variables is some aspect of the world which may have uncertainty. So capital R, is it raining? Capital T, is it hot or cold? So temperature, capital D, how long would it take to drive to work? And so on. We typically denote those random variables with capital letters. And variables are similar as they were in the constraint solving problems, um, where they have a domain. So in the case of raining, it's either raining or it isn't. It's either hot or it's cold. The how long does it take to drive to work probably isn't zero, but it is some number that's relatively small. So there probably is some minimum that could be figured out, but we'll say 0 to infinity. And L is the possible location. So if we were talking about in the case of Pac-Man, where is the ghost inside of the grid? It's somewhere inside of a series of quadrant locations. So talking about probability distributions, it is essentially associated, a probability that is associated with a value. So the probability of it being hot or cold, it may be even split distribution, although that's unlikely depending upon, I guess, where you live. The probability of it, the weather, is it raining or is it foggy or whatever else, may have some different sort of probabilities. Meteor is probably a non-zero probability, but it is probably very small. And then probability distribution, it's an unobserved random variables that have distributions. It's generally in a table of distribution values. And we typically, when we talk about a probability, it's a lowercase value, and basically just a number, not a series of numbers. Probabilities, typically all of them are greater than 0 and they all add up to 1. So those are kind of the characteristics of probability of given sort of conditions. And then moving on to joint distributions, it's over a set of variables, and it's a real number with the association of each of the outcomes. Generally speaking, you don't write them all out because it's basically something times something as a general rule. So it's going to be pretty big. Moving on to probabilistic models. A probabilistic model is a joint distribution over a set of random variables. Um, Random variables have domains. They're assigned something called an outcome, and joint distribution say whether assignments are likely or not, and they're normalized generally so that they sum up to 1. And ideally, only certain variables directly interact with others. And then there, as we talked about in the past, there are these constraint satisfaction problems. and their variables with domains, constraints, and so on. An event, it's basically something with an outcome, um, and it's based upon a joint distribution, and you can typically calculate the probability of an event. So what's the probability that it's hot and sunny? That's probably going to be pretty much more likely than hot and rainy, but who knows? And so on. So that's the key notation there is the probability of T comma W. So those are a joint distribution that is distinct. Well, and there's also the concept of a marginal distribution, which is basically a way of summing out or collapsing the rows, and so on, and by typically it's just simple arithmetic. Conditional probability is where it gets a little more interesting. This is the probability of A given B. So that can be calculated by the joint distribution divided by the distribution or the probability of a given the thing that is the second in the equation. So in this case, B, sometimes they're referred to as X and Y, and so on. So it's basically some math there if you want to work through the example, but that's the essence of it. And this becomes important, especially when we start getting into some of these other things, because they actually are pretty significant, especially in these conditional distributions. What's the probability that it's the weather and given a temperature equals hot? So a much higher probability for in that contrived case of it being sunny than it is that of it raining. And with that, we've talked basically through the concepts, the terminology of probability notation. Now we'll start talking about inference using full joint distribution. Basically, you compute a desired probability from known probabilities. So example, from a conditional, from a joint. You generally compute conditional probabilities, probability of on time, given there are no reported accidents, is 0.09. It's based upon a belief given some evidence, right? And so basically in this scenario, when we talk about evidence, we're talking about these things that are being viewed as being part of the conditional probability. And so when you add additional evidence, it potentially changes the outcome. So the probability of on time, given the probability of, or given that there are no accidents and it is 5 in the morning, really high, right? But if it's raining at 5 in the morning, then maybe not as high because you're probably going to drive slower, at least hopefully so. There's a way of calculating this through an iterative sort of approach through enumeration, but there kind of are some challenges with that, which is potentially it is computationally expensive. Anytime you have a big O with an exponential number in there, that's not good, either on time and space. So that's kind of the worst of both. Moving into the concept of independence. Um, so what does independence mean? Basically, one event does not rely or is influenced by a previous event. So two variables are independent if for all X and Y, the probabilities of X and Y is equal to the product of the probability of X times the probability of Y. So that basically they're factors of the two things is the basic idea. And another way of saying it for all X and Y, the probability of X given Y is equal to the probability of X. So basically what that's saying is that Y is not contributing to that probability combination at all. And the notation for writing it is given there as well. Again, the point of this sort of topic is to give you a high level overview of the field, not to make you a statistical sort of expert in this topic, and an example of independence. This moves us to Bayes' rule and why we use it. So the basic idea of it's basically you shift and redefine the formula, right? You're bringing piece of Y over and multiplying it by a given piece of X or Y. or given y. So the basic idea is that sometimes you want the conditional, or sometimes you have the conditional probability, but you want the joint probability. So it's a way of helping you do that manipulation. And the product rule, very much kind of similar to the same sort of concept. And then the chain rule, and this is basically saying you can always write any joint distribution as an incremental product of conditional distributions. And that becomes important whenever we start going through and calculating values using iteration. So the two ways to factor a joint distribution over two variables, and so on. So why would this be helpful? And some could argue it's pretty important. So moving on to conditional independence. So the probability of a toothache and a cavity and a catch. I'm not sure exactly what the catch is, but anyway, if you have a cavity, the probability that the probe catches it in it doesn't depend on whether I have a toothache, right? The same independence doesn't hold if I don't have a cavity. A catch is conditionally independent of a toothache given cavity. So the idea here is that there's sometimes things that are conditionally independent. Some additional sort of discussion of the topic. So there's a statement here that unconditional absolute independence is very rare. There's always some form of influence and impact between various other things. Conditional independence is our most basic and robust form of knowledge about uncertain environments. X is conditionally independent of Y given Z. So, and if and only if, the equation there. So the short of it is that most of the time things are not going to be truly independent. Going through this fairly quickly because we do have quite a bit to discuss. And you can apply the chain rule to conditional independence, which is useful again because we sometimes are doing this sort of thing through an iterative sort of process. And then the naive Bayes, and this is basically a way of doing inference using a naive sort of approach, also fairly useful. And with that, I'm going to stop our discussion of that chapter and we'll move on to the next.